Welcome you all to the Research Spark YouTube channel. This is the second and the last session of this fourth unit, that is the applications of linear ICs. So here is the outline of this session. Here we are going to talk about some more applications of your the ICs, that is optional amplifier particularly. So comparators, schematic trigger, non-sinusoidal oscillators. Then also we'll see the some filters, low, high, band pass and band reject. And then we'll see the waveform generators. So let's start. First, the comparator. So here comparator circuits is there. You can check the V. So in IC741 itself, there are two terminal 2 and 3 inverting and non-inverting terminals. So always if we'll use the the V reference at some inverting terminal, then what will happen? The output voltage will always depends on the the V reference, and if it is higher than that the V reference, then it will have the high voltage. Otherwise, the voltage will be the low. So depending on the the values, that is reference values, the output voltage will be the high or low. So that is why this is being called as an inverter circuit. Similarly, V reference can also be applied at the voltage reference can also be applied through the non-inverting terminal. So here again, if in the non-inverting terminal case, in this case, what will happen? If your voltage is high, then only you will be your volt. If your voltage is lesser than the reference voltage, in that case what will happen? Your voltage will be high, and if it is no, means if it is higher than that, in that case it will be the output will be the low. So this is the primary working principle of your comparator. Some another examples means we can also shift the V reference, and like here we can see the output voltage can be manipulated using the some more resistance. So in the right side, some other type of the comparator circuits are there. Now the schematic triggering. So schematic trigger or the bistable multivibrator uses positive feedback with the loop gain greater than the unity to produce the bistable characteristic. So like figure number 1, if you check, this is the schematic trigger circuit, and second one, just check, that is the voltage transfer characteristic as an input voltage increases. So as the input voltage will increase, then what will happen? The output voltage will be like if it is greater than the threshold voltage, in that case output voltage will be low, and if it is reverse, means like suppose if it is lesser than the threshold voltage, it will be the high voltage. So basically it's depend on the threshold voltage, and that is where the output will be low and high. That is why this is acting as a schematic triangle. And so see in the third graph, it's saying that the voltage transfer characteristic as input voltage decreases. Here, like if your input voltage, if you keep on decreasing, then what will happen? If input voltage is lesser than the threshold voltage, your input is your output is high. But if it is higher than that, the input your is low. So basically the gap, that is the gap in between VTL and VTS, that is the V threshold high and V threshold low, that is also called as the bandwidth or the width of your hysteresis, because this is actually working as a hysteresis effect. So where it is primarily being used, so if you will see, the normally we are using the street light. As for example, in the street light itself, we are using these type of the circuits. Why is it so? Because if your voltage fluctuation in this range, that is VTL and VTH, then what will happen? Since there is a width of this hysteresis, so if your voltage fluctuation in this range, means further your output will not be turned on and off. So basically it will prevent to turning on and off while fluctuating the small amount of the voltage in the street light. Now, next, non-sinusoidal oscillator. So, oscillator is primarily being used to generate the different types of the signals. So here, basically the non-sinusoidal oscillator can be generated using the IC 555. So if you will see the IC 555, then it have the 8 pins. So for like here is the circuit diagram of your IC 555 based oscillator. So how is it working? So just check here, pin number 1 to 8 are there. So comparator 1 is, there are the two comparator and one flip-flop RS, that is RS flip-flop, and then followed by the buffer circuit. So output is your buffer circuit, that is pin number 3. So comparator 1 is called threshold comparator, which compares its inputs with an internal voltage reference is set as 2 by 3V plus by the voltage divider R3, R4 and R5. When the input level exceeds the reference level, the threshold comparator output goes high, producing a high output at flip-flop terminal Q dash. That is another terminal. This turns the discharge transistor on, and an external timing capacitor starts to discharge. The internal control voltage node is connected to the external terminal. This provides the external control of the reference level. Should the timing period need to be modified when it is not active use, these terminals should be bypassed to ground with a small capacitance 0.01 microfarad to improve the circuit's noise immunity. Comparator 2 is also called the triggering comparator, compares its input trigger voltage to an internal voltage reference set to 1/3 of your input voltage by the same voltage divider as before in the comparator 1. When the output trigger level is reduced below this reference, the trigger compares output goes high using the same RS flip-flop to reset, and output Q dash goes low and the discharge transistor turns off. This comparator triggers on and on the leading edge of the negative going input pulse. So this way your signal can be generated using the oscillator. Now let's see some more examples, the applications that here it can also be used to the for low pass filter, then high pass filter, band stop and the band pass type of the filters. So first circuit is your high pass filter with the voltage follower, second one is the low pass filter with the voltage follower circuits. So if normally without using operational amplifier, if we wanted to design the RC, the high pass, low pass, simply we can use the RC components. So here also we are just using the RC, and the only thing is that we are amplifying our inputs, that is we are using the IC741, nothing else. And also the characteristic, if you will check for the high pass, then all our characteristics are also same. So TS, that is the transfer function, that is the output divided by input voltage, is equal to R divided by R plus 1 by SC. 1 by SC is the only the reactance across your capacitor. So finally it will be SRC divided by 1 plus SRC. So if we will plot these transfer characteristics, then that there will be the FL, that is the lower cutoff frequencies. If your frequencies falls to higher than to this FL, then definitely it will pass, and if it is not, then your high pass filter will stop to pass. So that is why this is being also called as a high pass filter. Similarly, for the low pass filter, low pass filters will allow the signals having the low frequency only. For high frequency signals, low pass filter will suppress or stop to pass to the output. And so also same as the normal circuits, here also we are using the RC components. uh, Here also, like that was the previous slide, contains the only first order. It can also be used as a second order low pass filter. The only advantage that the decay will be the very fast, means the cutoff frequencies, after the cutoff frequencies the your gain will be rapidly fall towards the 0. So second order, it contains the multiple or not multiple twice of the R components and along with the twice capacitance. And other things are similar. So first circuit is your two-pole high-pass butterworth filter, and correspondingly the board plots is showing the -20 and -20, that is -40 dB per decade. Similarly for the high pass also, second is your high pass, again here -20 -20, that is -40, that is +40 decade. Now some more application band pass just add the low pass and high pass, and you will get the band pass. Similarly just add difference, then you will get the band reject. So the bandwidth of your band pass filter will be your 1 by twice by RC, and the frequency will be 1 by twice by R into C, where R equivalent may be the square root of R2 and R3. So you can further check, that is the same process. You can find out the output voltage and solve it, and you will get these transfer statistics by using the V out by V in. Now voltage waveform generator, that is also called as a function generator or the signal generator, is an electronic device or circuit that produces electrical waveforms over a range of the frequencies. These waveforms are typically used for testing, development, and educational purposes in electronics and signal processing. So basically we'll have the basics of the oscillators here. The gain that can be written as AFS is equal to A divided by 1 plus A into BS. And if this is your we can call it as also T, which is equal to the A into B, that is the gain and the feedback product. So if it is equal to -1, then what will happen? Your feedback gain will be equal to the A, that is gain divided by 1 minus 1, and so A divided by 0, so it will tends to the infinity, and in this case your feedback gain will be the almost infinity, and never it will comes to the 0. So in that case it will continue to oscillate, and having advantage of these oscillations will have the different waveform or different signals. So this is also being called as a Brock-Hessian criteria. The criteria is the transfer functions T, that is the product of gain and the feedback, that is AB, should be equal to the -1. In actually it should be the little bit higher, otherwise it may drop to the 0 and it may not keep on continuing to oscillate. But this is the ideal case. Ideally it should be -1. Now some more examples of the oscillations. First is the phase shift oscillator. Here you can see and have in the circuits. Here it contains the 60 plus 60 plus 60 phase shift, that is 180, and always we are using the non-inverting, so always it will have the 180. So totally the phase difference will be the 360, means no phase. So frequency will be the omega naught is equal to 1 by square root 3 and RC. So this will be the frequency of this particular phase shift oscillator. Second one is your RC phase shift oscillator, and it will generate the frequency having the 1 omega naught is equal to 1 by square root of 6 and RC. Also the amplifier resistor ratio must be R2 by your R must be equal to 29, otherwise it may not be oscillate. So for the RC phase shift. Third one is the Wine bridge oscillator. Here we are using the some R and C, the resonance, the frequency, which will be equal to the omega naught is equal to 1 by R C. The condition is here, the magnitude condition is that the 1 plus R2 by R1 into 1 by 3, or R2 by R1 is equal to 2. Otherwise it may not oscillate. Apart from these oscillations, we'll have the different type of oscillations, so please go through the Hartley, Colpitts, and different type of oscillators. Thank you for listening me. If you have any doubts, please drop your comments. Since the session is being larger, so that's why I did not included some more oscillators. Please go through that. Thank you.